The end of the world had come, Judgment Day, divine intervention.
In the remote reaches of Siberia, a shocking discovery was made in a long-forgotten place and could change everything we know about energy.
They say that the Tunguska explosion had the force of more than 1,000 Hiroshimas.
Proof of ancient alien technology has been discovered, sparking theories that it might be the missing link to free energy.
While a milestone in temperature is good news for fusion, for net power to be produced, this heat needs to be sustained for long periods.
Could this be the breakthrough we've been waiting for? Tunguska explosion of 1908. On June 30th, 1908, a massive explosion shook the remote Siberian wilderness near the Podkamennaya Tunguska River. This event, known as the Tunguska event, is still the largest impact-related explosion ever documented. The blast is believed to have been caused by a meteoroid or comet fragment that entered Earth's atmosphere and caused destruction like never seen before or since. The explosion leveled an estimated about 770 square miles of dense forest, obliterating everything in its path. Trees were totally uprooted and scorched, radiating outward from the blast's epicenter in a pattern that resembled the aftermath of a nuclear detonation. Like and subscribe right now, and you'll have amazing luck for the rest of the week. The force was so powerful that it knocked down around 80 million trees, and the shockwave from the blast was reportedly felt as far as hundreds of kilometers away. Despite its destructive force, there was one thing that no one could explain. Where was the meteor? Eyewitnesses in the surrounding region provided vivid accounts of the event. They reported seeing a glowing fireball flying across the morning sky, followed by an ear-splitting explosion. It was something no one could ignore. A massive shockwave rippled through the area, strong enough to knock people off their feet even tens of kilometers away. Some described the sky as if it had split open, and right after, a scorching wind rushed through the area, burning trees and damaging structures in its path. Windows shattered, and crops were flattened as far as 40 miles from the epicenter, creating chaos and fear among local populations. With something so massive, you'd expect there to be an even bigger meteor waiting to be found, but that's the opposite of what happened. You could see the impact, but there was no meteor to be found. Scientists researching the area were at first totally baffled. They didn't know what was going on here, but then it became clear that whatever it was so strong that it didn't even have to physically touch the Earth to leave an impact. It was simply energy. After the physical search throughout the land proved that there was nothing there, scientists moved on to try to explain the explosion another way. They believed that it had to have been triggered by the airburst of a stony asteroid or possibly a comet fragment entering Earth's atmosphere at an incredibly high velocity. Upon entering the atmosphere, the object would have experienced intense friction, causing it to heat up very quickly and ultimately disintegrate at an altitude of 15,000 to 30,000 feet above the surface. The sudden release of energy from the object's destruction is estimated to have generated a blast equivalent to 10-15 megatons of TNT. This energy was not only 1,000 times more powerful than the Hiroshima atomic bomb, but also rivaled the largest thermonuclear tests conducted in human history. The airburst created a fireball brighter than the sun, and the explosion unleashed a shockwave that traveled through the atmosphere at supersonic speeds, flattening trees and causing seismic waves detectable thousands of kilometers away. It didn't stop there either. The airburst also released a significant amount of thermal energy, setting fire to the forest and scorching the ground in a wide radius around the explosion site. So, could this be the link to free energy? The energy released by an event like this, without relying on the typical nuclear or fossil fuel-based energy sources, just shows us the potential power of cosmic phenomena. which could provide an unprecedented source of energy if controlled or replicated. But how would we do something like this? One concept is that asteroid or comet fragments, like the one responsible for the Tunguska event, could be intentionally redirected or captured using advanced space technologies. Asteroids rich in kinetic and potential energy could be manipulated through gravitational assistance or targeted deflection to either safely disintegrate in Earth's atmosphere or be mined in space. These bodies contain vast stores of energy because of their high speeds and mass, and if we could harness even a fraction of the energy released during an airburst event, it could rival current energy production techniques on Earth. We don't even necessarily need it to power things on Earth. Scientists on Earth are even thinking about harnessing controlled energy releases from celestial objects like asteroids or comets to fuel space exploration and even deep space colonization efforts. By capturing and directing the energy from these cosmic bodies, we could totally change how we power spacecraft, potentially overcoming the limitations of traditional fuel systems. Instead of relying on finite fuel reserves, spacecraft could use the kinetic energy of these objects for near-limitless propulsion, opening new doors for long-term missions and travel to distant parts of the solar system. The challenge here is in developing technologies capable of managing so much power safely without risking the destruction of the spacecraft itself. But if we can get over that one hurdle, this method could be a game-changer, turning naturally occurring cosmic forces into a sustainable energy source for exploration, pushing humanity further into the final frontier with minimal resource consumption and maximum efficiency. It could be antimatter. There are researchers that think the explosion was caused by an object made of antimatter entering the Earth's atmosphere. Antimatter consists of particles that have opposite charges compared to regular matter, like anti-electrons and anti-protons. When antimatter comes into contact with normal matter, both are annihilated in a process that releases massive amounts of energy. So, the antimatter object would have collided with Earth's atmosphere, causing an annihilation event, which could explain the massive energy release and destruction seen in the Tunguska region. Antimatter has been very rare, but so have events like this. Who's to say that this particular event wasn't because of antimatter? And if it was, we'll have to figure out how to harness it to take things to a whole other level, unless it wasn't just antimatter. It might have been a mini black hole. The explosion was strange, to say the least. It's possible that it was caused by a small or mini black hole passing through the Earth. That's why we weren't able to see it in real life. According to this theory, a miniature black hole, which is an extremely dense region of space, where gravity is so strong that not even light can make it out of there, might have interacted with matter as it passed through the planet. This interaction could have released the massive energy that affected the Siberian forest. The idea hinges on the concept that black holes, despite their size, have immense gravitational forces that can warp space and time. A mini black hole, theoretically smaller than an atom but with a mass comparable to a mountain, could have caused the explosion by transferring energy through the atmosphere. However, for this to happen, such a black hole would need to pass completely through the Earth and exit on the other side, potentially even causing a second impact. If true, harnessing the energy from mini black holes could offer a nearly limitless power source, as black holes are capable of converting matter into energy with extreme efficiency. That is, if we can safely figure out how to get it done. But even if we just look at what's happened on Earth, there's a lot of room for research here. Because of the elemental anomalies. Research into the Tunguska event has uncovered traces of unusual elements in the affected region, like iridium and other rare materials. These elements are not typically found in significant concentrations in Earth's crust, which is one of the main reasons it is thought that this whole explosion has been a product of alien technology. Some scientists and theorists speculate that these anomalies could indicate unknown energy properties related to the object's composition. The presence of rare elements like iridium might even offer clues about the nature of the explosive event and its source. If the materials can be isolated and studied in detail, they could help us learn about energy generation or storage. For example, rare elements might have unique physical or chemical properties that could be harnessed for advanced energy technologies. Understanding these properties could lead to breakthroughs in developing new forms of energy or improving existing methods of energy storage and conversion. But these aren't the only things that we can use to harness endless energy. There's a lot more out there that can do the same thing. Like cosmic renewable energy. Cosmic renewable energy involves capturing and then utilizing energy from space, mainly through solar energy collected by satellites in orbit. This concept is based on deploying solar panels in space, where they can continuously receive sunlight without interruptions from weather or the day-night cycle. The collected solar energy is then converted into microwaves and transmitted back to Earth. This method offers a stable and nearly inexhaustible energy source, addressing the limitations of ground-based solar panels. Unlike Earth-bound systems, which are affected by clouds, space-based solar panels can operate around the clock. This technology could significantly enhance global energy security and sustainability, offering a reliable alternative to traditional energy sources and contributing to a cleaner, more resilient energy infrastructure. What's great about this method is that to some extent, the world has already made a major shift towards solar energy. We already have solar storage facilities, and a lot of the world has even moved on to have solar-powered electric car chargers. So this shift would be virtually seamless. Cosmic rays. Cosmic rays are high-energy particles, mostly protons, that travel through space and collide with Earth's atmosphere, generating secondary particles. These collisions can release a lot of energy, leading some researchers to explore the potential of harnessing this energy for power generation. The concept involves capturing the energy from cosmic rays and converting it into usable electricity. The problem here lies in developing technology to efficiently capture and convert the energy from these particles, given their high-energy nature and the diffuse way they interact with the atmosphere. Researchers are investigating various methods to detect and harness cosmic rays, including using specialized detectors or materials. If they end up successful, cosmic rays could provide a new and innovative energy source, supplementing traditional methods and contributing to a more diverse and sustainable energy portfolio. Nuclear fusion. Nuclear fusion, the process of powering stars like our Sun, can provide nearly limitless energy on Earth. Fusion involves combining light atomic nuclei, like hydrogen isotopes, to form heavier nuclei, releasing energy in the process. This reaction can bring us a potentially clean and abundant energy source with minimal environmental impact compared to fossil fuels. For this, we will have to get great at replicating the extreme conditions necessary for fusion, which means we need to recreate extremely high temperatures and pressures, but on Earth. Research efforts are focused on achieving this goal through advanced projects like the International Thermonuclear Experimental Reactor, which is working on setting up a sustainable and controlled fusion reaction. This and other fusion research initiatives seek to overcome the significant technical and engineering hurdles involved, including maintaining stable plasma and ensuring efficient energy capture. If they're able to get it done without any issues, this one method could totally change energy production, offering a stable and eco-friendly solution for meeting global energy needs. But sometimes you don't even need something to be present to get energy out of it. Zero-point energy. Zero-point energy is a fascinating concept rooted in quantum mechanics, representing the lowest possible energy state of a quantum system, even at absolute zero temperature. According to quantum theory, this energy exists in the vacuum of space because of the inherent fluctuations of quantum fields. Some researchers and theorists think that it might be possible to harness this zero-point energy for practical use. They think that this might be the power source that aliens might use to make their way to Earth, drawing energy from the fabric of space itself. But to get there, we'll have to do a lot of research. Even though hearing about the Tunguska event for the first time might make you feel like there can't possibly be anything else like it, that's not the case. There have been other incidents that are similar to it, and some are as old as time. Like the Vredefort crater. The Vredefort crater, formed around 2.023 billion years ago, is the largest confirmed impact structure on Earth. It resulted from a 3 to 6 mile asteroid. This impact created an initial crater estimated to be between 155 and 186 miles in diameter. Central to the crater is the Vredefort Dome, featuring uplifted granite and concentric ridges. Over billions of years, erosion has significantly reduced the original structure, leaving behind features like shatter cones and altered minerals. The exact dynamics of the Vredefort impact remain unresolved to this day. The crater's multi-ring structure, while characteristic of large impacts, challenges current models of impact formation. All of them are strange. It's very difficult to understand how such a massive and complex structure formed from a single asteroid impact involves reconciling the observed features with theoretical models of impact dynamics. Designated a UNESCO World Heritage Site in 2005, the Vredefort Dome is still being used as one of the most important sites to study ancient Earth and impact processes. Sikhote-Alin event. On February 12, 1947, a dramatic meteorite fall occurred over the Sikhote-Alin Mountains in Primorsky Krai, Russia. A massive iron meteorite, estimated at around 100 tons, entered Earth's atmosphere. As it came down, it produced a spectacular fireball brighter than the sun, visible across the region. The meteorite's fiery entry was paired with loud explosions and sonic booms at an altitude of around 18,000 feet. This explosion was so powerful it caused ground tremors and ignited forest fires. Unlike typical meteorite impacts, the Sikhote-Alin event caused over 100 craters, with the largest measuring about 85 feet in diameter and 20 feet deep. The sparsely populated area allowed for the recovery of over 23 tons of meteorite fragments, ranging from tiny shards to large pieces weighing several kilograms. This is one of the few times that a crater this massive still left pieces behind that could be taken in to study. The Caracas Impact Event. On September 15, 2007, at approximately 11:40 a.m. local time, a chondritic meteorite struck near Caracas in Peru. People saw it from all over the city, and as it came down, panic ensued. Even more when the meteorite made impact with the Earth. This impact created a notable crater surrounded by ejected material. Witnesses saw a bright fireball and heard a loud explosion, with the seismic shock damaging buildings up to 0.6 miles away. Following the impact, water was seen bubbling from the crater, and locals reported noxious gases. Many villagers experienced nausea, headaches, and skin irritations, initially thought to be caused by toxic substances from the meteorite. This made the earlier panic even worse. A toxic meteor? That sounded like an actual attack, but it was later found that these symptoms were because of arsenic vapors from the groundwater. The meteorite was key for us to understand meteorite impacts and their effects on both the environment and human health. Chelyabinsk meteor. On February 15, 2013, a meteor exploded over Chelyabinsk, Russia, in one of the most significant recent meteorite events. The meteor, about 59 feet in diameter, exploded in an airburst about 18.5 miles above the ground, releasing energy equivalent to 400 kilotons of TNT. The explosion produced a bright flash and a hot cloud of dust and gas. The shockwave from the explosion shattered windows and damaged buildings across 6 cities, causing injuries from broken glass and debris. The event was widely documented on dashboard cameras, capturing the fireball and subsequent explosion. What's insane about this particular crater is that the meteor that hit it was undetected before entering Earth's atmosphere. This proved that our defenses against meteors like this are just as bad today as it were millions of years ago. If anything, it's even worse, because despite having all the technology that we do right now, we still weren't able to detect this meteor before it actually made impact. Why? Well, that's something we still haven't been able to explain. And it's not the only one that defies explanation. There's also the Ulo crater. The Ulo crater in Bolivia's Andes Mountains is a geological feature that stands out because of its size and the surrounding volcanic rocks. The crater is about 1.6 miles long, making it a prominent depression in the landscape. Scientists have put forward lots of different theories about the crater's origin. One is that it could be an impact crater formed by a meteorite strike. But there is no meteor or even fragments of one ever found here, so it has to be something else. It might be the result of a volcanic explosion, possibly linked to nearby volcanic activity. A third possibility is that it's a caldera collapse, which happens when a volcano's summit collapses after an eruption. The presence of volcanic rocks around the Ulo crater complicates the whole thing. True origin, as both impact craters and volcanic features can look very similar. What is it really? Well, that's something we're still actively trying to find out. The Domaine du Météor. The Domaine du Météor in southern France is another geological site initially thought to be just a weird depression in the Earth, but has now been confirmed as a likely impact crater. The feature was first dismissed as a meteor impact site because of insufficient evidence. Recent studies by geologist Frank Brenker and his team have changed everything we knew about this place. They detected an anomalous magnetic field in the area, a sign of rock melting and resolidification typical of impact events. Not just that, but they've also found small impact spherules and shocked minerals, like diamonds, so it could be another meteor that we never saw coming. This confirmation is significant because small impact craters on Earth are pretty hard to identify. The Domaine du Météor's status as an impact crater makes this that much more important. While craters like this can be known for the destruction, which makes them kind of dark, the local winery has taken this in a more positive way. They've embraced this cosmic connection and now use it for marketing purposes. Lake Cheko. Lake Cheko is in Siberia, near the Tunguska event site, and is a focal point of debate because of its connection to the cosmic explosion of June 30th, 1908. Positioned about 5 miles northwest of the Tunguska epicenter, the lake measures roughly 1,600 feet long. Initially, everyone thought it was a natural feature, but the research has brought us closer to the theory that this is a potential impact crater from a fragment of the Tunguska explosion. Research conducted in 2008 by Luca Gasparini's team found young sediment layers, a conical lake bed shape, and magnetic anomalies that hinted at an impact origin. Controversy does still exist over its age and the feasibility of a stony meteorite creating a lake like this. While some studies suggested the lake is at least 5,000 years old, newer evidence points to radionuclide contamination from the mid-20th century, implying an age of at least 280 years. But not all craters have something to do with meteors. Some are even stranger. Like the Darvaza gas crater. Commonly known as the Door to Hell, this is a burning natural gas field located in the Karakum Desert of Turkmenistan, about 260 kilometers north of Ashgabat. With a diameter of 60 to 70 meters and a depth of approximately 30 meters, the crater was formed in 1971 when a Soviet drilling rig accidentally punctured a natural gas cavern, causing a collapse. To prevent the spread of dangerous gases, the rig was ignited, and the flames have been burning ever since. Despite efforts to put the fire out, the crater remains an active fire and a major tourist attraction, drawing around 10,000 visitors annually. It has also become a site for scientific exploration, where we can learn about unique extremophile microorganisms that have adapted to the harsh environment, making it one of the most interesting craters on Earth. So if you could only see one of these in person, which one would you choose?